Now let's consider unbounded integrals. This is the case where one of a or b is not bounded. So for example, a is equal to negative infinity, or b is equal to infinity, or this both holds. So a is equal to negative infinity and b is equal to infinity. So how can we estimate this unbounded integral when either one of them is not bounded between a and b, the integral from a to b of g of x dx? Note that we won't be able to sample the u's from a to b because one of a or b is going to be either negative or positive infinity. We're going to consider two possible approaches to this problem. The first one utilizes a change of variables technique and turns the unbounded integral into a bounded integration problem. And then we can solve the problem using bounded integration, which we just showed. The second method will evaluate the integral over a sufficiently large interval and then bound the remaining part by a small probability or a small value. So let's see an example and apply both methods. This example concerns the integral that we try to estimate, which is theta that's equal to the integral from 1 to infinity of 1 over x squared 2 plus sine x dx. So you can see that in this case, a is equal to 1, which is bounded, but the upper bound b is equal to infinity. So recall that the first approach we're going to apply is change of variables. So let's try to first apply that and transform this unbounded integral into a bounded integration problem. But now let's first review some calculus. So the change of variable technique for integration is also known as integration by substitution. And there's a theorem that is really useful here. Let phi denote a function on the interval between a and b for with a continuous derivative. In other words, phi prime, which is the derivative of phi, is continuous. Let's further suppose that g of x is a continuous function on the interval between phi of a and phi of b. Now, let's let x equals phi of y. Then the integral from a to b of g of phi of y times phi prime y dy is equal to the integral from phi of a to phi of b of gx dx, where x is given by phi of y. Okay. So let's go back to our example where we're trying to find theta that's equal to this thing. For here, our g of x is going to be 1 over x squared 2 plus sine x. And let's let our phi function, phi of y, which is equal to x, to be 1 over y. And we can find its derivative, phi prime of y, which is given by negative 1 over y squared. Now we can apply the change of variable technique. And we have that theta, which is equal to the integral from 1 to infinity of 1 over, so the original thing, is equal to the integral from phi of 1 to phi of 0 of 1 over x squared times 2 plus sine of x dx. And this, if we apply the earlier theorem over here, we'll be able to find that this is equal to the integral from 1 to 0 of 1 divided by, so this is replaced by phi of y, you can see. Phi of 1 over y squared times 2 plus sine of again, x is replaced by 1 over y, phi of y, times phi prime of y, which is negative 1 over y squared dy. And we can see that here, the 1 over y squared here and here cancel out. And we're left with the integral from 1 to 0 of negative 1 over 2 plus sine of 1 over y dy. And this is equal to, we flip this. So the integral from 0 to 1 of 1 over 2 plus sine of 1 over y dy. Now, we have transformed the unbounded integral problem earlier for x into a bounded integral problem, which we can address using our bounded integral Monte Carlo integration methods. So let's try to evaluate this theta, which is now equal to the integral from 0 to 1 of 1 over 2 plus sine of 1 over y dy. Let's try to implement this in R. Okay. So we have seen that after applying change of variable, instead of evaluating the original unbounded integral for x, we can now evaluate theta, which is equal to the integral from 0 to 1 of this function of y dy. And we can see that in this case, our a and b's are 0 and 1. So we evaluate this over the bounded interval from 0 to 1. To estimate this thing using Monte Carlo integration, we can apply the first method we have learned. Here, we sample our y's, y1 up to yn. Here, again, n is equal to 100,000 from the uniform distribution between 0 and 1. Then, we evaluate the function 1 over 2 plus sine of 1 over y. I call this function g star. So let's evaluate the function g star on each of the y draws we obtained in step 1. And the g star function is given by 1 over 2 plus sine of 1 over yi for each of the yi's. And in step 3, we can take the average of the g stars. And in this case, this will result in a theta hat, which is our estimate for theta. So here's the R code that implements this. In step 1, we draw the uniform 0, 1 random draws, so the y's. Y is going to be a length 100,000 vector, where each entry is a uniform 0, 1 draw. Next, we apply the function g star to each of the y's. So let's create a vector called g star of y, and that's equal to 1 over 2 plus sine of 1 over y for each of the y's inside the y vector. In step 3, we take the average and get our theta hat. In this case, we do mean of g star of y, and theta cat is approximately 0.446. Now, we mentioned before that there are 2 approaches that we're going to try for evaluating this unbounded integral. So we just tried the change of variables approach. Now let's try the second approach, which is breaking the integral into 2 parts. One of them is a bounded integral, and the other part is unbounded, but we can try to control its value to something that's relatively small. So let's try the other approach, where we break the integral into 2 parts. We were trying to evaluate theta, which is equal to the integral from 1 to infinity of g of x dx. And that is equal to the integral from 1 to m of g of x dx, plus the integration from m to infinity of 1 over, gx dx. So we break it into 2 parts, one part between 1 to m, and the other part is from m to infinity. Because sine of x is always bounded between -1 and 1 for any possible x value, we know that 2 plus sine of x is larger than 1, or greater than or equal to 1. So in this case, we know that its reciprocal, 1 divided by 2 plus sine of x, is bounded between 0 and 1. So what does this imply? This implies that our g of x function, which is the inside of this integral, is going to be less than or equal to or less than 1 over x squared for all possible x values. And the integral from m to infinity of 1 over x star of 2 plus sine x dx is going to be less than this integral from m to infinity of 1 over x squared dx. Where we replace this, we know that this part is less than or equal to 1. And we can see that this integral is equal to negative 1 over x evaluated at infinity and m, and that's equal to 1 over m. And you can see that as our m value gets larger and larger, the second part, the integral from m to infinity, which is bounded by 1 over m, is going to get smaller and smaller. For example, if m is equal to 100, then this second part is less than 1 over 100, which is 0.01. If m is equal to 1000, then the second part is bounded by 0.001, in which case it's going to get smaller and smaller to a point where it becomes relatively ignorable. In other words, we can view theta as the sum of a bounded integral between 1 and m and a small remainder that we can control. So in this case, we can control it under 1 over m. So now let's try to numerically approximate this using a relatively large m. In this case, m equals 1000. In step 1, we want to obtain draws from the first part. So we want to obtain draws of x1 all the way to x 100,000 from the uniform distribution between 1 and 1000. So between 1 and m. In this case, m is equal to 1000. In the second step, we try to get gx bar. So g of x bar is equal to 1 over xi squared times 2 plus sine of xi for each of the i's, each of the x draws. In step 3, we take the average of the gxi's and we multiply it by b minus a. So in this case, m minus 1, 1000 minus 1, which is equal to 999. So here's a code that implements this. First, we get x, which are random uniform samples, 100,000 of them between 1 and 1000. Next, we evaluate the g of x function on each of the x draws. Then we again get the theta hat by first calculating gx bar, the mean of the gx's, and then multiplying it by 1000 minus 1. And in this case, our theta hat is about 0.41, 0.42, which is quite close to 0.446 that we obtained using the other method. If you replicate this a couple of times, you will see that the results are going to fluctuate, but it's going to fluctuate around 0.44 or something like that. A question you might have is, why do we need to use Monte Carlo methods for integration? So you probably are thinking about, we have analytic approaches to these problems, and we can also use numerical quadrature, which is trying to approximate the area under the curve with all the small rectangles. Why do we need to obtain so many random draws from these distributions and try to estimate the integral? Well, the reason is that there are situations where Monte Carlo integration is the only viable approach. For example, there are many integration problems where analytic solutions do not exist. An example is the normal density, where you cannot really find an analytic solution to its integration. And the quadrature methods, which is the deterministic type of the numerical methods, where we divide the region into small grids, so small grids of, in the unidimensional case, of length d, it can suffer from curse of dimensionality. In other words, for univariate cases where we're just trying to integrate one variable, it works pretty well. However, for multivariable integration problems, the number of quadrature points, that is, the number of equally spaced intervals that we have to choose, will grow exponentially with the number of dimensions. So if you're doing the integration of two variables, x and y, you will need to consider equally spaced areas of a bunch of possible x values, a bunch of possible y intervals, and then the cross of each of them. So you can see that the number of quadrature points where you have to evaluate your function is going to increase with the dimensions. And when their dimension is super high, this method is not going to be efficient at all. However, the Monte Carlo methods can easily generalize to these settings. It works when the analytic solutions to the integrals do not exist. It also works in high-dimensional settings. So in these cases, the Monte Carlo integration could be really useful.